Yeah, yesterday we were discussing on the quantum mechanical treatment of the hydrogen molecular ion or H2 plus, right? Hydrogen molecular ion H2 plus, and this is a three-particle system with the nucleus A, nucleus B. Both of these nuclei are of hydrogens, and common to both nuclei, there is one electron. That is why it is S2 plus. Okay. Um, then we were examining this system quantum mechanically, and for that we assumed that the molecular orbital in which this electron is occupying, okay, was taken as a linear combination of the atomic orbitals. So we adopted the LCAOMO method, where the wave function psi, this wave function corresponds to the molecular orbital where the electron is occupying. Okay, this wave function is equal to A1 1 as A plus A2 1 as B. This is the linear combination of the two atomic orbitals. 1 as A is the atomic orbital of the hydrogen atom A, and 1 as B is the atomic orbital of the hydrogen atom B. Okay, then we took the linear combination of these atomic orbitals. Means each wave function is multiplied by some constant, and then it was added up, or then it is called a linear combination of these two atomic orbitals. Okay, so psi is an LCOMO. Then we applied the variation theorem. By applying the variation theorem, we reached two secular equations. The secular equations are given here. You have already gone through the secular equations in the previous class. If you didn't watch that video, I strongly recommend to go back to that video, watch that first, and then come back to here, because this is a continuation of the previous one. Okay, so this is A1HAA minus ESAA plus A2HAB minus ESAB is equal to 0, and there is another circular equation also, similar circular equation. Okay, so we got these two circular equations, and then we also simplified those circular equations by the relations HAA is equal to HBB, HAB is equal to HBA, and SAA is equal to SBB is equal to 1, SAB is equal to SBA is equal to S. Okay, we applied these relations in the circular equations, and then we reached two simplified equations, A1 HAA minus E plus A2 HAB minus ES is equal to 0. Okay, let me call this as equation number 2, and this was equation number 1, because we are going to use these equations for again. That is why I am giving the numbers here. Okay, and another circular equation, simplified circular equation, is A1 HAB minus ES plus A2 into HAA minus E is equal to 0. Okay, so these were the circular equations we obtained. Then we solved these circular equations. Means we equated the determinant of the coefficients of the A1 and A2 equal to 0. You may be remembering this if you watched the previous video. Then we got two solutions for energy. The energy solutions were E1 and E2. E1 has the expression HAA plus HAB divided by 1 plus S, and E2 has the expression HAA minus HAB divided by 1 minus S. Okay, and then we calculated the values of E1 and E2 for different values of internuclear distance R, and then we got two plots. Okay, this is corresponding to the plot of E1, and this is corresponding to that of E2. And in the case of E1, you can see that the energy profile reaches a minimum, and that minimum has the energy which is lower than that of the atomic orbitals of hydrogen atom. Here in this scale, we have taken the energy of the hydrogen atom, 1s orbital of the hydrogen atom, as EH. Okay, that is equal to 0. Okay, so we put the scale, the energy of the hydrogen atom, 1s orbital's energy at 0 in the scale, and then we can see that the energy corresponding to the minimum is even less than that of the atomic orbital. It means that when the molecule is formed or molecular ion is formed, H2 plus ion is formed, it can reach an energy level which is still less than that of the atomic orbitals of the hydrogen atoms. So this is a stable situation. And this stable situation is attained when the internuclear distance is 2.5 atomic unit. In this scale, internuclear distance is plotted. And here the energy is taken. Okay. So when the internuclear distance is 2.5 atomic unit, the energy is minimum. Okay. So that corresponds to a bonding situation, means that it is energetically it is energetically feasible for H plus and a hydrogen atom to come together to form H2 plus. Then it can sit at a lower energy level. So this is the equilibrium internuclear distance 2.5 atomic unit, which is equal to 1.32 angstrom from our quantum mechanical treatment. Okay, that is not the real value, but still we are doing a calculation based on certain trial wave function. So we have obtained certain value here. That value has been obtained by the calculations, and the value depends upon the trial wave function that we are using. Okay, if the trial wave function is very close to that of the original one, then the value will be better. Okay, anyway, we started with a trial wave function containing only two atomic orbitals. We can even include more atomic orbitals. Okay, but here we, just for the simplicity, we start only with the two atomic orbitals. And here the internuclear distance, equilibrium internuclear distance is 2.5 angstrom. And corresponding to that, there is an energy which is minus 0.6065 atomic unit less than the energy of the hydrogen atomic orbital, and this energy corresponds to 1.77 electron volt. It means that when H hydrogen atom combines with H plus ion, it saves 1.77 electron volt, means it is going to a stable situation. So it is feasible that this molecular ion can be formed. Okay, this is what we did yesterday, and we also saw that there is another energy, there is another solution for energy, and because this was a second order determinant, and it will have two solutions for energy. The next solution is E2, which is HAA minus HAB divided by 1 minus S, and if you are plotting this energy, then that energy profile will go like this, means E2 is always greater than E1. Okay, and you can see that at any equilibrium, any internuclear distance, the E2's energy will be always greater than that of E1, and also E2 energy is greater than that of the individual hydrogen atoms. So this is not a condition. If this molecule is in this state, this is not going to favor the bonding. Okay, so this corresponds to a bonding situation, and this doesn't favor the bonding. So we have two energy situations here. So since it is favoring the bonding, let me call E1 as E plus in the following discussions. The following discussions, I will put E plus instead of E1 because it is favoring the bonding, and I will call E2 as E minus. Okay, so let me write it as E plus. E plus is equal to HAA plus HAB divided by 1 plus S. Let me call this as equation number 4, and E minus, not E1 plus, E plus will be, okay, there is no 1 here. So E minus is equal to HAA minus HAB divided by 1 minus S. Let me call this as equation number 5. Okay, so we have two energy situations, and now we can look back. Now we can look back at the secular equations, I mean the modified secular equations, equations 2 and equation 3. Okay, here there is a term E in these equations. We can look only two for the moment. You can see that A1 into H, A minus E. plus A2 into HAB minus ES is equal to 0. So what is E? E can be either E plus, or E can be either E plus, or E can be E minus. അല്ലേ? ഇപ്പോൾ ഇക്ക് E പ്ലസും ആകാം, E മൈനസും ആകാം. അപ്പോൾ നമ്മുടെ ഇക്ക് E പ്ലസും E മൈനസും കൊടുക്കുമ്പോൾ നമുക്ക് രണ്ട് ഇക്വേഷൻസ് കിട്ടും. ഓക്കെ, ആ രണ്ട് ഇക്വേഷൻസിനെ നമ്മൾ സോൾവ് ചെയ്ത് കഴിഞ്ഞാൽ we will get two sets of values for A1 and A2. അല്ലേ? അപ്പോൾ ഈ ഇക്വേഷനകത്ത് നമ്മൾ ഇയുടെ വാല്യൂ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുന്നു. ആദ്യം E പ്ലസ് കൊടുക്കുന്നു, എന്നിട്ട് ഈ ഇക്വേഷൻ നമ്മൾ സോൾവ് ചെയ്ത് നോക്കുന്നു. അതിനുശേഷം നമ്മൾ E മൈനസ് കൊടുക്കുന്നു, അതിനുശേഷം നമ്മൾ ഈ ഇക്വേഷൻ സോൾവ് ചെയ്ത് നോക്കുന്നു. ഓക്കെ, അപ്പോൾ നമ്മൾ E പ്ലസ് കൊടുക്കുന്നു, then we will get a relation between A1 and A2 when we are giving the E plus. Okay, so that's good. If you know the A1 and A2, then we can substitute those values here in equation number 1, and then we get the value, then we get xi. So okay, here what you have to understand, that corresponding to E plus we will get a set of values for A1 and A2, and that set of values of A1 and A2 will lead to one particular value for psi, okay, or one particular expression for psi, and that expression for psi will be called psi plus, because that expression was obtained by substituting E plus in the secular equation. Okay, when we are substituting E plus in the secular equation, we get A1 and A2. That A1 and A2 is substituted here, then we get some psi values, and that psi is called psi plus. Then we will substitute E minus in this secular equation, and then again we will get a set of values for A1 and A2, and that A1 and A2 will be substituted again in equation number 1. Then we will get another expression for psi. That psi will be called psi minus. So our aim is to find out two wave functions corresponding to E plus and E minus. One wave function corresponding to E plus is called psi plus, and the wave function corresponding to E minus is called psi minus. Okay, so we are going to find out psi plus and psi minus. So how do we begin? We are going to substitute the values of E plus in the equation number, where the secular equation number 2. Okay, let me take equation number 2, and I will substitute the value here. So let me take the equation number 2 to down, otherwise it will be difficult for you to see this. Okay, we will take this equation, and then I will keep this equation down so that you can watch it again. Okay, I will keep it here. So we have this equation number 2 here. Okay, so I am going to substitute for E plus in this equation. Substitute for E plus. So let me substitute for E plus. Substitute E plus in equation number 2. Then I will get an equation A1 into HAA minus E. HAA minus E. What is E? In this case it is E plus. We are going to substitute E plus. So HAA plus HAB divided by 1 plus S. Okay, that is E, then plus A2 into HAB minus E into S. In our case, E is E plus, that is HAA plus HAB divided by 1 plus S into ES. Okay, into ES, because it is ES. Okay, so that is equal to 0. That is equal to 0. So let me expand this. A1 into HAA into 1 plus S minus HAA minus HAB. Okay, HAB, and then I have the common denominator for this one, that is 1 plus S. Okay, 1 plus s, 1 plus s, plus a2 into HAB into 1 plus s minus HAA into s, HAA into s minus HAB into s, minus HAB into s. Then I have a common denominator, that is 1 plus s, okay, and that is equal to 0. And now I can cancel the common denominator from both terms, or I can divide all the terms, the right hand side and the right hand side of the whole equation with the 1 plus s. Since the right hand side is 0, 0 divided by 1 plus s is 0 again. So I can omit all the 1 plus s in the denominator. So I get an equation a1 into HAA into 1 plus s. Then that is HAA in HA plus HAA into S minus HAA minus HAB, okay, plus A2 into HAB into 1 plus S, that is HAB plus HAB into S minus HAAS minus HABS, and that is equal to 0. So HAA minus HAA, these two will be cancelled, and here plus HABS and here minus HABS will be cancelled. So what is remaining? A1 into HAAS minus HAB, HAAS minus HAB plus A2 into HAB minus HAAS, and that is equal to 0. Okay, so I can write it again like A1 into HAAS minus HAB minus A2 into HAAS minus HAB is equal to 0. Now I have HAAS minus HAB, HAA minus HAB in both terms, so that's a common factor. So I can write like HAAS minus HAB into A1 minus A2. A1 minus A2 is equal to 0. Okay, and this indicates that A1 minus A2 is equal to 0, or A1 is equal to A2. Okay, so now we have reached reached to get the relative values of A1 and A2. We don't have the absolute values of A1 and A2 here. We know what is A1 in terms of A2, okay, and what is A2 in terms of A1. We only know that A1 and A2 are equal. Okay, we don't have the value of A1 and A2 so far. We know the relative values of A1 and A2. Okay, now we have to get the absolute values of A1 and A2. Then only we can substitute the value of A1 and A2 in our equation number 1 and get the value for psi plus. Okay, so in order to get the value of A1 and A2, now what we are going to do is we are going to apply the normalization condition. The condition for normalization. We have a molecular orbital. The molecular orbital is psi. Psi is our molecular orbital. And this psi is a normalized molecular orbital. It means that integral psi square d tau is equal to 1. This is a condition for normalization. Condition for normalization. Okay, so the molecular orbital square, the integral of the molecular orbital's wave function square is equal to 1. And it means that integral, what is psi square? A1 1 as a plus a2 1 as b. A1 1 as a plus a2 1 as b, the whole square, d tau is equal to 1. It means that integral a1 square, right? A1 square 1 as a square d tau plus a2 square integral 1 as b square d tau plus 2a1 a2 integral 1 as a 1 as b d tau is equal to 1. Okay, so a1 square into integral 1 as a square d tau, what is that? That is also equal to 1 because the atomic orbital 1 as a atomic orbital already is normalized. Okay, so integral 1 as a square d tau is equal to 1. So we can write it as a1 square into 1 means a1 square plus a2 square into integral 1 as b square d tau. 1 as b is the atomic orbital of the hydrogen atom B, right? So that is also a normalized atomic orbital, and therefore integral 1 as b square d tau is also equal to 1. So we can write it as a2 square into 1 plus 2a1 a2 into integral 1 as a 1 as b d tau. What is integral 1 as a 1 as b d tau? We already know that. That is called yes. That is called yes. Integral 1 as a 1 as b d tau is yes. We gave this this notation yesterday for integral 1 as a 1 as b d tau. Okay, so a1 square plus a2 square plus 2a1 a2s is equal to 1. Okay, then we already know that a1 is equal to a2. a1 is equal to a2. So we can write it like a1 square a1 square plus a2 square is also equal to a1 square plus 2a1 a2, that is equal to 2a1 a1 or a1 square, yes, is equal to 1. Okay, it means that 2a1 square plus 2a1 square yes is equal to 1, or we can write a1 square plus a1 square yes is equal to 1 divided by 2, or a1 square into 1 plus s is equal to 1 divided by 2, or a1 square is equal to 1 divided by 2 into 1 plus s, or a1 is equal to 1 divided by root of 2 into 1 plus s. Okay, root of 2 into 1 plus s. Let me write it better. Okay, 1 plus s. Okay, so that's the value of a1. And since the value of a1 is equal to this one, the value of a2 is also same, because we know that a1 is equal to a2. Therefore, a2 is equal to 1 divided by root of 2 into 1 plus s. Now we have the values for a1 and a2. You will have to remember that we got these values for a1 and a2 when we substituted for E as E plus, E plus values. Therefore, now we can substitute these values for A1 and A2 in our psi MO. So psi MO, or the molecular orbital wave function psi, is equal to A1 1 as A plus A2 1 as B. You remember this. This is equation number 1, right? Equation number 1. So we are going to substitute here in equation number 1. Psi is equal to A1 1 as A plus A2 1 as B. So since this is obtained by substituting E plus in our equation, we call this as psi plus. Okay, therefore psi plus is equal to A1 1 as A plus A2 1 as B. That is equal to 1 divided by root of 2 into 1 plus S 1 as A plus A2. A2 is equal to 1 divided by root of 2 into 1 plus S 1 as B. Okay, or we can write it like 1 divided by root of 2 into 1 plus S into 1s A plus 1s B. Okay, so this is the molecular orbital psi plus, and this psi plus molecular orbital corresponds to the energy E plus. Okay, now we can substitute the value of E minus, the value of E minus. So we can substitute the value of E minus in our equation. Okay, we will substitute this value of E minus in our equation. We can substitute in the same equation here as we substituted for E plus. We can substitute in the same equation. Where is that equation? Yeah, here. In equation number 2, we can substitute for E minus. You can do the similar procedure. You can do the similar procedure, and then you will get the value for A1 and A2. Then that A1 and A2, when you are substituting there, will be 1 divided by root of 2 into 1 minus s. So in that case, A1 and A2 will be 1 divided by root of 2 into 1 minus s, and in that case you have to see that A1 will be equal to minus A2. Okay, so what we can do is we can substitute those values there. So let us substitute the value of E minus in our equation. Where is that equation? Here. Yeah, this equation number 2. Again, I will put that equation number 2 down. Okay. I will take this equation, and then I put this equation here. And in this equation we will substitute for E minus, and E minus is HAA minus HAB divided by 1 minus S. So let us substitute for E minus here. Okay, so A1 into HAA minus E. In this case is E minus. E minus is HAA minus HAB divided by 1 minus S. Okay, 1 minus S plus A2 into HAB minus ES. That is, E in this case is E minus, that is HAA minus HAB divided by 1 minus S into S, that is equal to 0. So we can write it like A1 into HAA into 1 minus S, okay, minus HAA plus HAB I'm not going to write the denominator here. You know what is the reason? We already did it in the previous steps, right? So that denominator will be cancelled. That's why. Plus A2 into HAB into 1 minus S, okay, minus HAA plus HAB into in these cases we have S also. Okay, so HAA into S and HAB into S is equal to 0. Okay, now we can write it again like A1 into HAA minus HAA into S minus HAA plus HAB plus A2 into HAB minus HAB into S, okay, and minus HAA into S plus HAB into S is equal to 0. These are the terms to be cancelled here. HAA plus HAA minus HAA. Okay. Then from here we can cancel minus HABS and plus HABS. So what's remaining? A1 into HAB minus HAB minus HAAS, okay, plus A2 into HAB minus HAB minus HAAS, that is equal to 0. Okay, now you can look at this equation. We have HAB minus HAAS as the common factor in both terms, so we can write it like HAB minus HAA into S as a common factor into A1 plus A2, okay, is equal to 0. It means that A1 is equal to A2, no, sorry, that is equal to A1 plus A2 is equal to 0 and A1 is equal to minus A2. That's what I said a couple of minutes ago. In this case, A1 will be equal to minus A2. In the previous case, when we substituted for E plus, in that case A1 was equal to A2. Here A1 is equal to minus A2. Okay. So again, if you are applying the condition of normalization, and in that condition for normalization we substitute for A1 and A2 there, okay, then what is the condition for normalization we obtained here? Where is that condition for normal? Psi square d tau is equal to 1. Then we took that equation where we got a1 is equal to 1 by root 2 into 1 plus s here, and just because we substituted here, okay, a1 square is equal to a2 square, like that. So here we have a small difference here. Up to here we have everything okay. A1 square plus 1 a square, okay, this expansion. Then we reach A1 square plus A2 square plus 2A1 A2 into S is equal to 1. Up to here it is okay. After that we have to substitute for the other case. So I take this one. A1 square plus A2 square plus 2A1 A2 into S is equal to 1. Let me copy this and put it down. I'll put it here, okay, in this equation. And this equation was obtained by the condition of normalization, and in this equation we have to again write a1 square plus a2 square, and a1 square and a2 square will both will be what, a1 square, because a1 is equal to minus a2, so a1 square will be equal to a2 square. So a1 square plus a2 square, we can write it like a1 square, a1 square plus a1 square plus a1 into, in place of a2 we have to substitute minus a1, okay. So we have to give 2a1 into a2 is equal to minus a1 into s is equal to 1. So we can write it like 2a1 square, okay, plus minus 2a1 square, okay, into s is equal to 1, okay. So we have a minus sign there, and we can write it like a1 square minus a1 square s is equal to 1 divided by 2, and a1 square into 1 minus s is equal to 1 divided by 2, and therefore a1 square is equal to 1 divided by 2 into 1 minus s, okay, and therefore a1 is equal to 1 divided by root of 2 into 1 minus s, okay, 1 minus s, okay. Here we got 1 divided by root of 2 into 1 minus s, 1 minus s. In that case, the other case where we substituted for e plus, In that case, we got 1 divided by root of 2 into 1 plus s. Okay, so this is a1. Therefore, obviously a2 will be a2 is equal to minus a1. There's a minus 1 divided by root of 2 into 1 minus s. Okay, so now we can substitute a1 and a2 in our psi equation. Psi is equal to a1 1s a plus a2 1s b. Psi is equal to a1 1s a plus a2 1sb. So let us substitute for a1 and a2 here. That is equal to 1 divided by root of 2 into 1 minus s 1 s a. Now a2, that is minus 1 divided by root of 2 into 1 minus s into 1 s b. Therefore we can write it like 1 divided by root of 2 into 1 minus s into 1 s a minus 1 s b. So this is the equation for psi when we substituted the value of a1 and a2 by giving e as e minus. So let me call this as psi minus. So this is psi minus. So psi minus is equal to 1 divided by root of 2 into 1 minus s into 1s a minus 1s b. Now here we have two expressions for the wave function psi. The first expression was, what was that? It is here. Okay, we got an expression for psi plus. Psi plus here. Psi plus is 1 divided by root of, let me copy this. Okay, so psi plus is 1 divided by root of 2 into 1 plus s, 1s a plus 1s b, and psi minus is equal to root of 1 divided by root of 2 into 1 minus s into 1s a minus 1s b. The other equation is here. Okay, so these are the two equations. One is 1s a and the other one is for 1s. One is for psi plus and the other one is for psi minus. Okay, so we have two equations here. The two equations are for, sorry, okay, two equations here. Let me put the my box was not very good. Maybe use a better box. Okay, so these two equations. So we got two equations or two expressions for the molecular orbitals. What does it mean? We started with psi and we have reached two expressions for psi plus and psi minus. And we know that in the case of psi plus, the energy corresponding to that is E plus, which leads to a minimum. And in the case of psi minus, energy leads to E minus, which is always higher than that of the atomic orbital energy. So one is actually leading to, we can actually assume now that this orbital corresponds to the bonding and the other orbital corresponds to the anti-bonding. Okay, if the electron is occupying the psi plus orbital, okay, if the electron is occupying the psi plus orbital, then the situation will be stable, and if the electron prefers to go to the psi minus orbital, then the molecule is going to break. Okay, so this is the bonding situation and the other one is anti-bonding situation. So this is what we can see by combining two atomic orbitals, which are the atomic orbitals we used one as a atomic orbital, one, sorry, I am always taking wrong options. Okay. One is a atomic orbital and one is B atomic orbital. Both are the lowest energy atomic orbitals in two hydrogen atoms, right? The hydrogen atom's lowest energy atomic orbital is 1s orbital. After that we have 2s, 2p, then 3s, 3p. Like that we have many orbitals. Okay, and here we have taken only the lowest energy atomic orbital 1s a and 1s b, and when we are taking the lowest two atomic orbitals and linearly combining them, it leads to two molecular orbitals, psi plus and psi minus. So the linear combination of two atomic orbitals will lead to the two molecular orbitals. Okay, Linear combination of two atomic orbitals will lead to two molecular orbitals. That is why we have already learned in our previous classes that two atomic orbitals combine to give two molecular orbitals like that. Okay, so this is the theory behind that, and actually we can include more orbitals. These are basis functions. Okay, these are basis functions, and here we have taken only two basis functions, and we can take more basis functions. For example, we can include 2s, 2p, etc. We can include more basis function, and if you are including more atomic orbitals, we will get correspondingly more molecular orbitals also. Okay, the more the number of basis sets, the better will be the result. Okay, so this is what we have done here just by taking a trial function by linearly combining two atomic orbitals. Okay, and here the trial wave function actually led to a situation. It theoretically explained why the hydrogen molecular ion is stable. Okay, it theoretically explained. It gave a quantum mechanical explanation for the molecule formation, and it also shows that the electrons, instead of occupying the atomic orbitals, will occupy the molecular orbitals. Okay, and here the molecular orbital has been obtained mathematically by combining the atomic orbitals. And since the trial wave function is not very good, the results may not be so much good. Okay, there is enough scope to improve these molecular orbitals. But anyway, this is a good beginning for you, that we can apply quantum mechanics to define the bond. Okay, we have not yet reached the physical interpretation of this one, but we have a mathematical expressions here, and here from these mathematical expressions we can see that the molecular orbitals can be formed and the electrons will occupy these molecular orbitals, and this will correspond to the low energy situations, means it will correspond to bonding. And in the next class I will show you the physical interpretation of these wave functions, so how these wave functions can be plotted, or the square of the wave functions can be plotted, so that how we can see the electron density between the two nuclei and all these things in the next class. Okay, I hope you enjoyed this class, and thank you for watching, and bye.